Hey, and welcome to today's webinar. My name is Isabella. I'm from OPTUM GX, and I am happy to welcome you to this session. Today we are focusing on consolidation in OPTUM GX. If you have any questions during the webinar, feel free to ask them in the Q&A, and we will get back to them by the end of the webinar. I will send you a recording of today's session on mail, so if you have any colleagues or any team members that you would want to share this webinar with, you can do so tomorrow. And today we have Christian. He's a partner here in OPTUM GX, and if you have joined us before, you know that he's really good at explaining everything GX related and also geotechnical related. So we are in good hands like the other times. And if you have, again, any questions, he will pick up at the end of the webinar. So just feel free to ask them. And with that, I will hand it over to you, Christian.
Thank you, Isabella. Thank you for the kind introduction. We'll see how it goes. This is sort of a somewhat complex subject because it's somewhat complex in its own right, and it's not necessarily straightforward to have complete compliance between the classical Terzaghi way of doing consolidation and then the way that it's typically done when it comes to finite elements, which talk about Biot consolidation. So I'll be talking a little bit about that today, how to sort of make sense of classical quantities in a finite element program in GX. So this is a brief outline. There'll be some consolidation theory, Terzaghi, that's the classical theory, and then what I call Biot, what is a little more general and contains Terzaghi as a special case. And then moving on to consolidation in GX. How is it done? What models should be used? There's something called creep, which is sort of an add-on, you could say, to consolidation that I'll also be demonstrating, and then some examples, not very elaborate examples, just in a way more sort of getting started examples. So consolidation is a very, very classical subject. It's sort of one of the first things possibly that was studied somewhat theoretically before there was ever even anything called geotechnics by Terzaghi and others in Austria in the 1920s, I believe, something like that. There's an interesting paper, actually. I was going to mention that, but I forgot about it. The Terzaghi-Villinger dispute that is quite interesting. It's published in Geotechnique. But anyway, it's a very classical subject, and the example people always show is the Leaning Tower of Pisa. So that's been sort of tilting over for centuries. It was stabilized a while ago, so now the tilting has sort of stopped or maybe even reversed. But this is often taken as an example of consolidation. I think it's consolidation, but I think it's a bit more than that as well. Maybe some creep. But anyway, it's gradually settling in an uneven way into the ground. And so the sort of the key ingredient when it comes to consolidation is the effective stress principle, which sort of says that the effective stresses are the total stresses minus the pore pressures. And we know that deformations are a result of changes in effective stresses, not total stresses. So the idea is as follows. You have a saturated porous medium, sort of shown schematically here. It's not a real material, but nevertheless, you have some particles and you have some fluid, some water in between the particles. You compress this box, and then you measure what happens, and you measure that with respect to time. So you can have sort of a stress axis up here and then the time axis here. And so the first quantity you plot is the total stress. That you apply the total stress and then it remains constant. So that just is like that. And then you can measure, for example, if you measure at the middle of the sample somewhere, you will see that the pore pressure, as soon as you apply the external stress, it also shoots up to the same level. And then gradually, as the water seeps out through the edges here, that's the idea, that these edges are permeable, then you will see that the pore pressure, or the excess pore pressure, as we call it, the pore pressure in excess of whatever hydrostatic pressures there may be, dissipate. They tend to go back to zero. And then the effective stress principle basically says, well, the effective stress evolves something like that. So it's zero to start with, and then it gradually increases to become equal to the total stress. And as deformations are a result of changes in effective stress, well, they change in time, so the deformations change in time as well. They will follow a curve like this as well. So that's basically consolidation. And what happens, of course, is that the solid skeleton is gradually compressed, and the water is then squeezed out of the material. And this happens more or less quickly, depending on the permeability, on the hydraulic conductivity of the material, and the stiffness of the solid skeleton is also part of the whole story. So Terzaghi's 1D consolidation, it typically it involves a sort of a 1D kind of compression test like this. The dashed line here is supposed to indicate that the water can drain freely from the top boundary here. There's also a version where it drains from both the top and the bottom. And the classical result is that the evolution of the pore pressure with time follows this equation here, the so-called diffusion equation, or the heat conduction equation. That's sort of a classical textbook result, where CV is the so-called coefficient of consolidation. So the larger CV is, the faster things happen. So that's a quantity that can be determined on the basis of an experiment like this. There's various techniques of doing that. From a more theoretical point of view, it can also be related to the hydraulic conductivity and the stiffness of the material. So for a linear elastic material, it can be shown that CV is actually this quantity here, E, the Young's modulus, times the hydraulic conductivity, and then divided by gamma W, the unit weight of water, and then there's some Poisson's ratio effect as well. Now, soils are, of course, not really linear elastic, so the utility of this here, this relation is maybe quite limited, but it can be used, of course, to benchmark your final element programs, for example, which we have done as well. So then stress-strain behavior, that's also sort of a classical way of a classical result is that you see that, and I'm talking here about the stresses. So you apply the stress, you wait for things to consolidate, and then you read off the deformation, apply another stress, wait for full consolidation, and then read off another deformation again. And if you do that, you'll typically see that you get sort of a stress strain curve that looks like this. So it gets stiffer. The more you compress it, and you can also plot. So, and this is sort of this is also an important point. This is sort of a loading branch. If you were to unload, it would happen something like this. So there's a big difference between loading and unloading in terms of stiffness. So this is how it would typically look. What you can do is instead plot it in terms of log stress versus strain, and then you tend to get something that is not exactly straight lines, but often not too far from it either. And since in geotechnics we sort of kind of like to often switch the axis around, you could plot it like this, and then now I think it starts to look familiar. So strain versus log stress. And instead of strain, void ratio is often used. So the void ratio is, the changes in void ratio is sort of proportional to strain. So you start at some void ratio, and then as you compress the material, it decreases. And you have this unloading, reloading branch here as well. So if you plot this, these data in terms of void ratio versus log of the applied stress, I should have really written log 10 here because that's what is usually meant by log. You get this curve, and the slopes of these are what we call the compression and swelling indices, respectively. So these are kind of inverse. These are kind of compliances. So the larger this is, the less stiff the material is. So this line here, we call this the normal consolidation line, and these are unloading, reloading lines with a smaller compliance, so a higher stiffness. And so the idea is that if you start at some some point up here, say you have sort of a slurry, and then compress the material, well, you will move down this normal consolidation line. And if you were to unload, well, it would happen like this along an unloading, reloading line. And if you were then to load again from this point here, well, then you move along the unloading, reloading line until you hit the normal consolidation line, and then you move on that. So this kink here, where you initially unload it, is kind of a characteristic quantity. It's known as the pre-consolidation stress. And the ratio of your initial stress to your pre-consolidation stress, or the other way around, is what we call the over-consolidation ratio. So if we are starting at a stress here that is lower than the pre-consolidation stress, well, the material is over-consolidated, meaning it's stiffer initially until we hit the normal consolidation line. So the OCR is always greater than or equal to 1. Here, in this case, starting from here, it's greater than 1. And if we were always remained on the normal consolidation line, well, then it would be equal to 1. Right, so we would just move like that. There's an infinite number of unloading, reloading lines, but if we don't unload, we don't really know about them. So that's I think the textbook material, and that's what we kind of would like to also replicate in GX, or at least have as a reference to the kind of analysis when we do analysis. And that's what we've tried to sort of pay quite a close attention to the with respect to the models that we recommend for consolidation analysis. But before I get into that, I want to just show you the general theory that is used in OPTUM GX, and that is used in, I think, pretty much all finite element programs. It's usually goes under the name of Biot, who sort of came up with a more general, you can say, not just consolidation, but sort of, I think it's called pore mechanics, so the interaction or the behavior of fluid saturated materials. And the equations are the ones shown here, and I don't want to make too much of a story about it, but just to say that it's kind of the usual equations. Equilibrium, we always have that. Then the principle of effective stress, that's also, you could say, non-negotiable. Strain displacement relations, there's nothing unusual about those. And we need also some stress-strain relations. Something like this. This C here could be nonlinear, or it could be linear, it could be anything. But what is the new thing, and what really sort of is what makes consolidation what it is this equation here, which is a combination of basically mass balance and Darcy's law. So PE here, I've switched notation because in finite elements, U is the displacements, PE here is the excess pore pressure, and epsilon V is the volumetric strain. So basically what this says is that changes in volumetric strain lead in one way or another to changes in excess pore pressure. And that's the squeezing of the material. The material compresses, and then something happens to the pressure. So this is the key component, what makes the, what you could say, couples everything. And I did sort of a diagram to see how the different sort of quantities here couple. So we have the excess pore pressure, and the volumetric strain here. So in this equation, this mass balance plus Darcy's law, the excess pore pressure, well, that is part of the principle of effective stress. The total stress is also part of that, which is also part of the equilibrium equations. The principle of effective stress also involves the effective stress itself, which of course also is part of the stress-strain relations. So everything is coupled like that. And if you look at epsilon V, the volumetric strain, well, that is related to the strain displacement relations, and also eventually to the strain displacement relations, yeah, and to the stress strain relations. So everything is kind of coupled here. Changes in volume results in changes in excess pore pressure, which results in changes of effective stress, which eventually results in change in deformations. So that's how it works. This general theory contains Terzaghi as a special case. I've actually already shown it, the 1D compression for a linear elastic material. There's complete one-to-one correspondence. But Terzaghi doesn't really move beyond 1D. And so if you want to do something more than one-dimensional columns, then this is the way to go. The stress-strain relations, I've just written them like this. But this theory is really applicable to any model for linear elasticity, more Coulomb, and also the one we recommend if you were to do sort of consolidation that is as close to the classical kind of Terzaghi type consolidation as possible. Then I think the modified Cam-Clay model, our version of the modified Cam-Clay model, I have a few words about it shortly, is really the way to go. How do you actually activate it? How do you actually do it in GX? And there's two things you need to be aware of. There's this setting drainage, which there's various options here. There's an option called drained, undrained. We say that means that in the short term, excess pore pressures are generated, in the long term not. When it comes to consolidation, well, if you want excess pore pressures generated, then the material has to be drained, undrained, the drainage setting. And always drained, well, no pore pressures are ever generated. So these are important settings. And then there's the time scope setting as well. We have long-term, short-term, and then we have something called variable. And I will now switch actually to GX. I think that's probably better to show these. And I have an example already set up. It's a very simple example. It is an example where we have a kind of an embankment. We start with this situation, and then we activate the embankment. So we put a heavy load on this soil here, which is supposed to be kind of like a clay-like material. Has a Young's modulus of 5 MPa, so not a lot of strength. C and phi, it's a more Coulomb material. C and phi of 5 kPa and 30 degrees, and it has a hydraulic conductivity 10 to the minus 3. It's been set to, and the drainage setting here is drained, undrained. And then there's the always drained, that non-porous is really if pore pressures are not relevant at all. So if you have a material, a non-porous material, of course, pore pressures are not relevant. But this is drained, undrained, meaning that pore pressures indeed are generated, whereas the fill here, the embankment, I've set that to always drained. So that's a kind of maybe a gravel or some sort of sand type material that's dumped on top here, and that it doesn't generate pore pressures. And so that's for the materials. And then the way it works is that we calculate the initial stresses here as usual, and then we have a deformation analysis where the effects of this embankment are accounted for. And so then there's the time scope settings. And as I mentioned, we have long-term, that's the default setting. And that's the setting you use in many cases, of course. Short-term, that is the conditions at time equal to 0 with excess pore pressures generated where relevant. And then there is a setting called variable, where you can run, for you enter the time, the number of days it is in this case. I think you can have a choice of units, but the default is days, so 100 days, and we use 10 steps. And then there's this step variation, constant linear. Constant means that, well, you go 0, 10, 20, 30, and so on. Linear means that it is the steps are smaller to start with, and then they gradually get bigger, which is typically what you want for consolidation, where most of the action happens initially, and then it kind of phases out. In G2, for those of you who have used that, we have a separate analysis type called consolidation. In GX, it's part of deformation, and then there's this variable time scope that basically activates it. So I will try to run this just to show you that it actually does run. So then we run through the 10 steps here, and eventually we get then the results. And if we plot the displacements, for example, we can do the U numerical, why not? And then you see that it evolves something like this. There are these settings up here, so you can either be on scale or on step. So scale means that you are within a single step 0 here. You can also do like that. So you basically just magnify the deformations here. That's maybe not always very interesting. Well, the more interesting is to see how things evolve in time, and that's you choose step there, and then you see it evolves like that. And you see you have actually already at step 0, you have some deformations. Those are the initial short-term deformations that you get immediately when you apply the load, and then after 100 days, so that's 15 millimeters, and then after 100 days, well, you're up to about twice that. You can also, and I think I forgot to say that's always a good idea before you run a consolidation analysis, especially if you have a large problem. It's always a good idea to just try to run a long-term analysis first. So there you get the long-term and also a short-term analysis. So these will give you results corresponding to the short-term here, to what we had initially for the consolidation analysis. So that was, yeah, well, here I will do like that. So that was the initial deformations, and these ones here should be, oh no, these ones down here should be the same. Okay. I should have, of course, started these from, should look like, not from stage 2, they should start from stage 1. And this one should also start from stage 1. Yeah. So we run the initial stresses and the consolidation, and then we do a long-term and a short-term. Should have done that to start with, but nevertheless, so here we have the short-term from a single step short-term analysis, which are sort of identical to the ones from the first step, the immediate settlements for the consolidation analysis. So it's just a good idea to see how do things look in the short term and in the long term. If you have settlements of tens of meters, then maybe, it might not be worth running the full consolidation analysis. Or if things are not even stable, then of course, forget about it. Okay, so that's pretty much how it works. And I would like to just switch back to the presentation and just say a few words about the CAM-clay model, because that is the model we recommend for consolidation. It's the one that is closest to classical consolidation, even though any model can be used. So what is the CAM-clay model? Well, in PQ space, for those of you who are familiar with that, this is sort of a more Coulomb failure line. In CAM-clay land, it's called the critical state line, but it is, in our sort of interpretation of the CAM-clay model, it is actually a regular, more Coulomb failure line. You cannot cross that. And then we have these hardening caps that are these ellipses that are here. So you move from an initial state, and then if you move up sort of like that, well, then you gradually activate these hardening caps, and they have the effect, or they are calibrated, you could say, to basically change the stiffness so that you have not a linear elastic, perfectly plastic behavior, but you have sort of a gradual decrease of stiffness as you approach the ultimate limit state. The parameters of the CAM-clay model. So the CAM-clay model replicates a behavior in isotropic compression. So in the case where we have equal stresses on all equal compression on all sides, that is like this, which is sort of similar to what we are used to, right? But except it's a little bit different, because in CAM-clay, first of all, it's not log 10, but it's ln. That's just a kind of you could say that's an easy conversion. But in CAM-clay, it's this relation is formulated with respect to the mean stress, the mean effective stress, whereas classically in odometer tests and so on, we make reference to the vertical stress. And it's not so clear in a odometer test what the relation between the mean stress and the vertical stress is. Actually, there's not a one-to-one. It changes typically as you compress the material, and the stresses don't necessarily grow. The vertical and horizontal stresses don't grow at the same rate. So it's somewhat problematic to convert the CAM-clay relations to the more classical ones. You can try, and we have tried. We've done the best we could. So you can do it sort of in an approximate fashion. But the CAM-clay parameters, deformation parameters, we call them lambda star and kappa star. They're equivalent to our compression and swelling indices, CC and CS. So we have validated this CAM-clay model pretty thoroughly. It should be on the website. And so for a 1D isotropic compression test, when it looks like this, analytical, the orange, and GX, the blue lines. When it comes to a odometer test, well, things are a little bit more problematic. We can only really sort of replicate. Well, if you believe that a classical test is straight lines, which it really isn't, but if you say that's what it is, then you can only sort of replicate that in an approximate fashion. You can make this conversion between the kappa and lambda and the CS and CC parameters. It's the conversion here, so there's something with the void ratio. One uses strain, the other one uses void ratio. To the 2.3 is just ln10. And then some people say there should be factor 2 up here. Some people say that this relation here is approximate and this one here is exact. I think, to the best of what I can sort of gather, this is how it is. They're both exact, they're both approximate. And the factor of 2 here, well, in some cases, maybe you get better fits, but in general, I think these are are the better conversions. So in GX, we have, so this is the exact same problem as before, except that the clay down here is now a modified can clay material. I've used kappa star and lambda star, these values here. But there is a choice of parameter set. You can choose set B, and that gives you CS and CC. What happens internally is that these are converted to lambda and kappa using the formulas there that I showed you before. So the same thing is done. It's just if you're more familiar and with if these are the values you have at hand, well, then you don't have to do a manual conversion. Of course, you should be aware of what is actually done, and what is done is that they are converted according to those equations I just showed before. And then let's just run that as well. So the modified can clay, it takes a little bit longer than typically than the more Coulomb to run. Some iterations are needed in each step, and the equations are generally a little bit heavier, but I don't think it's too bad. So this also ran for 100 days, and well, with the deformation parameters I've chosen, which I haven't really chosen, I've just used the default ones, we get somewhat larger displacements, I think, than before. 130 millimeters at the end. So that's good. And I wanted to also we have it's a sort of a debut of of a new plugin, XY plotter, because it could be nice to plot. You see, I put some result points down here. So these can now be plotted with this tool here. So we have points 1, 2, and 3. And if we just, so it's in stage 2, and we can plot then for result point 1, the deformation versus time, the vertical settlement versus time, and 2, it's a little bit less, and at point 3, which is even deeper in the ground, it's a little bit less again. And you can see a lot happens to start with, and then it sort of levels out at some stage. The rate decreases, and we eventually get to the fully consolidated state. I think this was at something like 90, was it 96%, 94% degree of consolidation. That's number here is calculated as an average for the domain, so it should be taken with a sort of a grain of salt. But usually, it's a good indication of the state of things. So those were the deformations. We could also look at the excess pore pressures. And here there's a little bit of a funny thing, because you can see the color scale up here. That is kind of set to the last stage here, where the excess pore pressures are very small. They are, of course, largest in the first step, and we can then change to, there's another setting per step color range. So the color range can be fixed on the basis of the whole series, the whole time series, or individually within each step. So individually within each step, we see that we have 32.7, so we can then change back to the whole time series, but with an upper limit of 33, and then see how that evolves. And that evolves in this way. It's over pretty quickly. It's pretty large to start with, especially right here under the center of the embankment, and then it gradually sort of fizzes out with time. Yeah, so that's how that works. A few other things that I think are relevant is that the situation here with respect to where does the water seep out. The rule is that it seeps out on three boundaries. If you don't do anything, this is a drainage boundary, and this is kind of a drainage boundary as well, in the sense that this is a always drained material. So this is a material where the excess pore pressures are always zero. So once the water comes up here, well, it dissipates. But you can also apply manually excess pore pressure boundary conditions, and that's what I've done down here. At the bottom, that's this feature here, fixed excess pressure, and the fixed value is zero in this case. So this is basically this is a drainage boundary as well. So suppose at some depth in the ground you have some material where you think some porous material where the water can drain freely into. And that, of course, makes a difference as compared to what we did before. So without this drainage boundary and with it, if we plot the results, it's already running. I should then say refresh and clear. And then I have my model, model 2, that's the one from before, at result point 1, so that's the one up here at the top. And then stage 3, that's the one with the fixed excess pore pressure equal to 0 here at the bottom. And we should expect that to drain faster. And it does drain significantly faster. The drainage height, if you like, is halved, and we know there's something with the drainage height squared, right? So it happens a lot faster. In the same way, if you want to model drains, also can do it like that. So in a case without drains, it's the case from before, and then some drains where as soon as the water hits these drains, well, it dissipates. And that is something that also is sort of very equivalent to this situation here. It's clear. And then the initial one, and then the one with drain, you can see that really makes it go quickly with the configuration that I have shown here. Good. Last thing I wanted to say something about was this business with creep, because sometimes you have materials that consolidate and everything looks as if it's sort of on the way to full consolidation, and then nevertheless the deformations just keep growing. The Leaning Tower of Pisa is sort of an example of it, probably. There's a limit to how long it can take for water to drain out from some soil layers, and I think 8 centuries you probably shouldn't be at 100% consolidation, and yet it continues to settle. And so this sort of effect can be modeled with what is known as creep, and creep is an option of the Cantlay model. You activate it down here. You say creep yes, no, and then there's a creep constant. It's in the manual, which is also online or will be shortly. But this is a very classical way of doing it. You have this creep index mu that you specify as a fraction of the compression index, and this is a value I've chosen, 0.02, which usually shouldn't be very high at all. And then, so this was the original Cantlay, and then the exact same thing except with a bit of creep. And if we look at the situation there, and I've let this run actually for not 100 days, but 200 days. And let me just refresh. And model A, stage 2. Plot that. That's what we saw before. We have some initial settlement of course, 15 millimeters or so. Actually, you can see the data in here. 14 and then to 126 millimeters. And you can see it's really quite leveled out now at 200 days. And if we go to model B, the one with creep, well, what you see then is that things kind of just continue. The deformations continue to grow. Slower and slower, but nevertheless, they do continue to grow. So that effect can be taken into account in that way. I think I've covered everything I wanted to say. Of course, this analysis type deformation with time scope variable can be used for much more complex and interesting problems than the ones shown here. It should be straightforward to do so in 2D, 3D axis symmetry, with or without structural elements and so on. So there's nothing really special about it other than the setting here needs to be set correctly. And then I think it's also reasonable to pay some attention, obviously, to the model you use and to the parameters. And I would suggest the modified CAM-clay model in most cases. So that was it. And I will take any questions there may be.